When we talk about the specific kind of binary tree called a binary search tree, there are a few more important terms we need to be comfortable with. Now, with a binary tree, there cannot be any more than two immediate child nodes under any one node. Now, a node can certainly have two child nodes, which themselves each have two child nodes, which themselves each have two child nodes, and so on ad infinitum, or at least until you run out of memory. But those are the restrictions. In a binary tree, a node can have 0 child nodes, in which case it's a leaf, or 1 or 2. Why this limitation? Well, for one thing, it gives us clarity. We know that in a binary tree, any node object can only contain two links, two references to children. It won't contain some arbitrary array of links, maybe 1, maybe 14, maybe 574 child nodes we have to iterate over. No, just 2. And in a binary search tree node, those two links have specific names. They are the left child and the right child. It may help to think about it this way, that every node will always have two links, the left child and right child link. But those links might be null, meaning there's no children. This node is a leaf. Or the left child link might point to another node, or the right child link might point to another node, but not the left, or both left and right might point to other nodes. Now, why do I seem to be laboring this point? Well, because in a binary search tree, it matters whether a node is added as the left child or the right child. And it's not just, oh, it's the first child node, put it on the left, put the second one on the right. That's not the way it works here. Because in a binary search tree, there are reasons why a child node is inserted at either the left or the right position beneath its parent. You see, a binary search tree is not some random collection of stuff all strung together. It is a data structure that naturally stays sorted without the immense amounts of reshuffling that would be needed in a basic array. And actually, a binary search tree is sometimes called a sorted tree or an ordered tree. And here's the first rule of binary search trees, that a left child node must be less than its parent, and a right child node must be more than its parent. And that rule follows all the way down. As we insert new nodes with values, that is the rule that will always be followed to make sure that the tree stays sorted. And the example I'm showing, I'm just using an integer here as the representation of what's stored in a node. Binary search trees are often used to store key-value pairs like an associative array, so what we'd be representing here is the key to an object, and it's the key that would be stored in order, in sequence, in a binary search tree. So any entry here must be unique. You can't have duplicate keys, just as you don't have duplicate keys in a hash table or even an array. So we create a binary search tree by adding one node, one key-value pair, and let's say its key is 50, so it is the root node. And then we want to add a new node. This has a key of 25. The binary search tree evaluates it, says, well, this is less than the root, so it goes in as the left child. Then we add another node. This one, coincidentally, has a key of 100. It's evaluated. We see that it's more than the root, so it goes in as the right child. Then we add a new node. It's 75. Again, it's more than the root, so we'll go down towards the right and we'll compare it to the next one. There is something already there in that right position. We compare again. Well, it's less than this node, number 100, so we'll insert that as the left child of 100. Then we add another node. This is 30. Well, it's less than the root. We'll go down and compare to the one on the left. Well, it's more than that node, so we'll put it in as the right node here. Let's add a smaller value. We'll add the number 10. We'll compare it to the root. It's less. We'll go down and compare it to the value on the left-hand side. Well, it's less than that as well. We go down again and we'll put it on the left-hand side of the 25 node. Adding some larger values like 1,000, well, that's going to be added as the right child of the right child. We add the number 2,000. It's on the right all the way down. We add the number 3,000. That's going to be on the right all the way down again. But of course, data structures aren't just used to store elements. We need to be able to retrieve. And this is what binary search trees are good at. We now want to find if the binary search tree contains an object with a key of 2,000. We follow the same rules. We'll compare it to the root node. It's more than that, so we'll head down to the right. It's more than that one. We'll keep heading down to the right. It's more than that one. We'll keep heading down to the right till we find it or we figure out it's not there. But each time we're heading down one path, we're discarding entire sections of the tree, so it's a very quick way to find a specific element. The other benefit is binary search trees are staying sorted. If we retrieve the items in a left to right sequence, we will get them all out in order. Now, you've probably noticed that we have more levels of nodes on the right-hand side than on the left. Now, it's not unusual for this kind of thing to happen. We can't always guarantee that the way data is added will allow us to build a tree with a perfectly symmetrical structure all the way down. In this case, we say that our tree is unbalanced. There are more levels on one side than on the other. The downside of this is it means, on average, we would have to perform more checks to find or insert or delete any values on the right-hand side than we would on the left. Now, we are talking here about the abstract idea of a binary search tree data structure. So do understand that there are several implementations of this binary search tree idea that are self-balancing binary search trees. They include algorithms so that as the tree becomes unbalanced, and it will, it's going to be reorganized to more equally divide the number of levels. Now, this can be something as simple as shifting the position of the root node to reorganizing the entire tree. But the important idea with balancing a binary search tree is not that we always need two child nodes. That part of it doesn't matter. It's more important that the number of levels are roughly equal to each other. We don't have 3 levels on the left and 20 on the right. When you start implementing binary search trees, you'll come across common self-balancing binary search tree algorithms that have names like red-black trees, AVL or Adelson-Velsky and Landis trees, splay trees, scapegoat trees. Now, in this course, I'm not getting any deeper into these because they take us away from data structures and into the algorithms that manage data structures. That's quite a different matter and quite a different level of depth. This is still an area you can go ahead and get a couple of PhDs in. So what are the main benefits? Well, binary search trees are fast for insertion, they're fast for deletion, they're fast for accessing any element, even at large sizes. But you might think, well, hash tables are apparently good at that too. And that is absolutely true, but because binary search trees stay sorted, what these do that hash tables don't is allow us to get all the items out of the tree in order, to enumerate everything in sequence, which typical hash tables don't provide. And when we start looking at particular languages, trees aren't an area you'd expect as much direct language support as with other data structures. You typically don't just instantiate an object of a binary search tree type, because we're getting into an area where binary search trees may be being used, but they're being used behind the scenes to implement some other data structure. For example, the C++ implementation of a set data structure is done with a binary search tree. You don't need to care. You don't need to think about left child nodes and right child nodes and whether this is balanced or not. You just use the set. Now, likewise, in C# and .NET, there is no binary search tree class, but if you use a sorted dictionary, a collection of key-value pairs with the keys in order, that is using a binary search tree to implement that idea. Now, while dictionaries are often implemented with hash tables, if you want to keep your keys in a sorted order, hash tables aren't really any good at that, and binary search trees are. Now, Ruby has no built-in tree data structure. There are some third-party implementations, and likewise, Python doesn't have a built-in tree data structure. With Java, we have classes like TreeMap that stores a collection of key-value pairs, but if you read some of the documentation, it'll tell you this is a red-black tree. That's a self-balancing binary tree. And folks, that is all I'm going to say about binary search trees in this course, but next I'm going to cover the heap data structure that also uses a binary tree for implementation. So onward and upward.